Lesson 2.6, Data Estimation and Prediction. In this lesson, we will see how to use MATLAB to perform data estimation tasks. The previous lesson was on data classification. Estimation is highly related to classification, and many methods used for classification are also relevant for estimation. Estimation involves the use of one or more features or measurements of a process that are observable to attempt to estimate the value of some other feature or features associated with the process that may be difficult to observe directly. So the only difference is we want to predict a continuous feature rather than a discrete classification as is done in classification tasks. In the classification lesson, we showed how MATLAB can be used to easily create ad hoc classifiers in code or to implement methods like principal components analysis for prediction in code. We ultimately saw how there are a suite of methods built into MATLAB that use prediction models. In this lesson, we will demonstrate the use of several different built-in prediction models for data prediction. However, classification and prediction follow the same fit-predict framework, and it's important to note that the same approaches for creating classification functions can be applied to data prediction. And vice versa. The data prediction methods we demonstrate here could also be used for classification. Okay, let's go into more detail about data prediction and start by looking at a simple example. Let's say we are a car manufacturer designing a new car. We have a pre-existing data set containing specifications and fuel efficiency for previously produced cars. Perhaps we would like to predict the fuel efficiency for our new car that we plan to make based on its expected vehicle weight and horsepower using this pre-existing data set. This would be a typical estimation or prediction problem. While we cannot measure the fuel efficiency of a vehicle until it is built so that we can directly test it, we can estimate what it will be using some known observable quantities in an existing data set. Let's go to MATLAB and look at some examples of data estimation methods. As before, we will look at some examples with the Fisher's iris dataset. We use the unique function to get a number code for each of the three species. In the following examples, we'll consider the fourth feature in mesh as our response variable that we want to predict. So we set y equal to the all rows fourth column of the measurements matrix. Y is what we refer to as our response variable. Now let's set up our features. We will try to estimate y using the other features in mesh and the species code S. It's also quite common to have a large set of features where some of them may not be helpful in estimating a response variable or are redundant. To simulate this, let's also include some redundant features and some that we don't expect to be predictive of y. To do this, for our fifth feature, let's include a second copy of feature 1 with additive random Gaussian noise with zero mean and standard deviation of 0.2. Let's also include as a sixth feature another entirely random noise vector in our feature set. Since we're using random numbers, if we want our code to be repeatable, we first need to seed the random number generator using RNG before sampling the random numbers. Okay, so we have our feature set and our response variable set up. We will evaluate several prediction methods with this data set. Each method will use some data to train the estimation method. Then we will want to see how well the method performs. It's best practice to have a separate testing set to evaluate the method performance that was not used to train the method. This is because a common problem is overfitting of the prediction approach to the training data, as we saw with support vector machines in the last lesson. So by holding out some training data, we can observe whether our estimation approach has been overfit to the training data by confirming the method performs similarly on the testing data set, which is withheld from the training process. So we can define a training set to contain half the data from the odd numbered rows in the data set. That leaves half the data for testing. But even after training with a training set, some methods have hyperparameters that need to be tuned to optimize performance. For this process, we would like to use what typically is referred to as a validation set. We optimize parameters on this validation set, and finally, we'll have an independent testing set to show how the method works with unseen data that is neither used for training or parameter tuning. So we'll take half the remaining data on every fourth row of the data set, starting from the second row, as our validation set. And keep the other half on every fourth row, starting from the fourth row, as our testing data set. Okay, now that we have curated our data set, we can see how some methods built into MATLAB perform when using our feature set. Our feature set, again, includes the first three iris features, plus the species classification, plus a redundant vector, plus a random vector. And we use this to estimate our response variable, which is the fourth iris feature. So first we try the simplest approach, which is linear regression modeling, which was introduced in the last section, using the fit-lm function in MATLAB. With this function, we provide the training features in the train X matrix and training response variable in the train Y vector as the first and second arguments. Linear regression methods model features as continuous variables, whereas discrete variables are treated differently and termed categorical variables. So, for any discrete valued variables, such as our species label feature, it is important that we inform the fit-lm function that it is a categorical variable. We do that by using the categorical vars flag, followed by an array of indices to the feature numbers that represent categorical variables. Aside from the species, all of our other features are continuous, so our array only contains the number 4, since the species label is the fourth feature in our feature set. And once our model is built, we can use the predict function to see what values for the response variable are estimated for new features. In this case, we will look at the features of the testing set as input. This results in predicted values for the response variable based on the value of the features input into predict. Since we know the true answers for the response variable in the test set, we can measure how accurate the predictions are. A common metric on the performance of an estimation method on a test set with known true values is called the mean squared error, or MSE for short. We measure the squared difference between the true and predicted value for each example in our test set. And this gives us a vector containing the squared magnitude of the error between the prediction and the true value for each example. And then we compute the mean of this quantity across all samples. In MATLAB, this is simply mean of the squared difference between the prediction vector and the true response vector test y. We can see that our prediction method results in mean squared error with the true value on our test set of around 0.03. We can also plot the results to visualize how good of a prediction method we have. Scatter plots are the most common approach for visualizing the accuracy of an estimation method. So first we open a new figure. Then we plot on the x-axis the true value, and on the y-axis the predicted value. We can use red stars as symbols. And label the axes with the true value on the x-axis and the model predicted value on the y-axis. With this plot approach, a perfect estimation would result in all data points falling exactly on a diagonal line in the plot. So let's show a perfectly diagonal line. We can do so by finding the range of the data in both the x and y directions. We can find the range using the min and max functions. And then plotting a line with x values going over this range and y values going over this range using a black dashed line. Since the true values are on the x-axis and a perfect estimation would fall exactly on this diagonal, the error in the prediction is seen as the vertical distance from each data point to the dashed diagonal line. Next, we can also compute the Pearson's correlation coefficient between the true value and the estimation. Recall from the lesson on visualization that diagonal-shaped scatter plots indicate correlation between two data sets. This correlation that we can see in the plots can also be quantified using Pearson's correlation coefficient, which captures how diagonal the data are. The correlation coefficient is close to 1 for two quantities that are highly correlated, in other words, two quantities that have a scatter plot shape that is very close to positive diagonal. The coefficient is -1 for two quantities that are highly negatively correlated, or close to 0 for uncorrelated data. Correlation tests also produce a statistical p-value that permits hypothesis testing on whether the correlation between the data sets is statistically significantly different from 0. Typically, we consider a p-value less than 0.05 to mean that the correlation is significantly different from 0, and thus the two quantities being tested are indeed correlated. In this case, we do find a strong and significant correlation with a correlation coefficient very close to 1 and a very small p-value. Let's wrap our display method up in a function that we can reuse so that we don't have to repeat this code. Our function estimation error plot will take as input a prediction vector as well as a target vector. First, we compute the mean squared error. Which is the mean squared difference between the prediction and the target. Then we produce the scatter plot. And whatever the current plot axes are. Label our axes with the true value on the x-axis and the model predicted value on the y-axis. We find the range of the data using the min and max functions. So that we can plot our diagonal with black dashed lines. And we can compute the correlation coefficient between the target and the prediction, which we can report the results of that in a title. And finally, we can add a legend. Okay, let's use it. First, let's clear the current figure. And then we call estimation error plot with our linear model prediction and our testing set response variable as inputs. From this display, we can see a simple linear regression model does quite well. We have mean squared errors of 0.03 for predicting sepal width measurements based on the iris species and other available measurements. Inspecting our model, we can see that there are a number of variables with insignificant p-values. That is, features 1, 5, and 6 all have p-values larger than 0.05. When we learned about using linear regression for feature selection, we saw that when we have terms in our regression model that are not statistically significant, This means that we have some features in our feature set that are either not correlated with the response variable or they are redundant with other features. So, to obtain a more compact and less noisy set of features, we can use stepwise regression. Here we can use the stepwise ln function with inputs train x, train y, and we'll use it to build a model in a stepwise fashion, starting with just the constant term, which is indicated by this constant argument, and then in a stepwise fashion adding up to an upper limit of all possible linear terms, which is indicated by the upper and linear arguments. Finally, we indicate that feature 4 is a categorical variable. Similar to the previous fit-lm call. We find that with using stepwise regression, we arrive at a model that includes features 1 through 4. With all of these features found to be statistically significant for estimating the response variable. Features 5 and 6 were removed. And recall, we chose feature 5 to be a redundant feature and feature 6 to be a random, uncorrelated feature. So stepwise regression has correctly removed these two features and left only the original measurements in the resulting model. Alright, how accurate is stepwise regression in estimation? We can use our estimation error plot function. And we see we get virtually identical mean squared errors of around 0.03, slightly lower at 0.028 with this reduced feature set. We also get a very similar scatter plot and correlation between the prediction and the true values. So this dataset lends itself well to linear regression for estimating the response variable. We would say there is a highly linear relationship between the features and the response variable. But what happens if we do not have a linear relationship between the features and the response variable? For example, what if the response variable has a highly discontinuous relationship with the feature data? To explore this, let's create a synthetic response variable that has such a property with our feature set. We will add discontinuities in each continuous feature based on its value being larger or smaller than the mean of the training set. So first, we compute the means of each feature in the training set. We store this in the MNS variable. Then we define our response variable as a partitioned linear function of the features by adding a constant when each feature is greater than its mean value. So first we have feature 1, and then we add the constant 2 whenever the value for feature 1 is greater than its mean value. Then we'll have feature 2 plus the constant 10 whenever the value for feature 2 is greater than its mean, plus feature 3 plus 50, constant 50, when the value for feature 3 is greater than its mean, plus feature 4, plus the constant 100 when the value for feature 4 is greater than its mean. Let's also limit our feature set to the first 4 features, as we know these are the features that are associated with our new response variable. So we redefine our train X, validate X, and test X feature sets. We also need to redefine our training, validation, and testing versions of our response variable. Okay, now what happens when we try to use stepwise regression for this new response variable? First, our stepwise linear model finds feature 1 to no longer be significantly associated with the response variable, so it is removed from the feature set. Next, we can look at prediction errors on the test set. We can see that the resulting model produces mean squared errors of almost 70 on the test set. We can also see from the plot that many data points diverge from the diagonal, showing substantial prediction errors. This is expected because we have intentionally defined the relationship between the features and the response variable to contain discontinuities not well modeled by linear regression. While the data are indeed mostly diagonal, and so we still see a high correlation coefficient, the scale of the errors is much, much worse than before. With our original data set, mean squared errors were 0.03. Now, with discontinuities in the relationship between our response variable and the features, our mean squared errors have increased by 3 orders of magnitude to almost 70. In this scenario, other estimation methods should work better. Regression trees are a machine learning method that handle discontinuities easily. The method aims to find discrete partitions of the feature space to estimate the response variable. In MATLAB, to train a regression tree, we have another fit function like the linear regression model fit-lm. This is the fit-rtree function, which can be used in a very similar manner, with the training feature set as the first input, the training response variable as the second, and we also specify categorical variables with this function using the categorical predictors argument. To get a sense for how this method works, we can use a built-in regression tree visualization method to inspect the resulting tree. We can see the view function permits displaying the decision tree. To predict a new response value with a new feature vector using the decision tree, we start at the head decision node, and if the value for x4, which is feature 4 in our data set, in a new feature vector is equal to 1 or 2, then we move down the tree to the next decision node along the left branch of the tree. Otherwise, if it is equal to 3, we would move down the right branch to that decision node. Assuming we go to the right decision node, if the value of feature 2 is greater than or equal to 3.05, we go down the right branch and the decision tree terminates in a leaf node that estimates the value of the response variable to be 180.4. Otherwise, we trace down the other decision branches until we arrive at another leaf node that estimates the value of the response variable. One will note that there are a discrete number of leaf nodes. There are 13 leaf nodes in this case, meaning that this method chooses between 13 possible values for the response estimate. For example, let's try predicting values for two unique feature vectors. We'll define a vector with features 0, 3.1, 3.5, and 3. So with this feature vector, we trace down the tree to the leaf node, estimating the value of the response variable to be 180.4125. Also, if we use the vector 0, 4, 3.53, we can see we trace the tree to exactly the same node. While this may seem somewhat limiting at first, in practice it often works quite well and permits handling large, discontinuous changes in the response variable for small changes in features. For example, with x2 decreasing from 3.1 to 3.0 and x4 changing from 3 to 2, our predicted response decreases by an order of magnitude to 11.5. There are some hyperparameters we can set when using fit-r-tree that can affect how the tree is constructed and ultimately optimize the estimation accuracy of the method. For example, let's investigate choosing the maximum number of splits and minimum parent size. The maximum number of splits is controlled with the max num splits parameter, and the min parent size parameter determines how many training observations must contribute to the learning process for each decision node. We can use the validation set that we held out until now to evaluate how the choice of these parameters affects our prediction accuracy. Since we have two parameters, we will have a 2D search space. Note that since the parameters are generally not independent, that is, the choice of one parameter will affect the choice of another, we need to vary both parameters, resulting in the 2D search space. In the prior lesson, we did some informal parameter tuning. Now, let's try to do parameter tuning in a more systematic, formal fashion. We will define a 20 by 20 grid of parameter options in our 2D parameter search space to test the accuracy of the method for all combinations of 20 values for each of the two parameters. Our errors will be stored in the variable error. Then we can use nested for loops to evaluate each of the two parameters. Within the for loops, we compute the regression tree model. For this example, I set the max num splits variable to 3 times I. So we will have a maximum of between 3 and 60 decision nodes, since I ranges from 1 to 20. Then the minimum parent size I set to j plus 1, so that it ranges from 2 to 21. After building the model, we use it to estimate the response variable on the validation data set. We can then compute the mean squared error between the prediction and the true values of the response variable in the validation data set. And that result goes into our error matrix. After the for loops run, we can visualize the result as a surface plot. Where our x-coordinates range from 2 to 21, and our y-coordinates will range from 1 to 20 times 3. We can use the log function, which can compress larger heights of the surface and make lower minima easier to visualize. We can label our axes. And view the results. We're looking for the combination of two parameters that results in the minimum errors. From the plot, we can see that for this application, our minimum parent size must be small. And then as long as our max num splits is at least 30, we get the most accurate predictions. We can use the find function to get the indices to all of the ij combinations that minimize the errors. We can see that there are many locations that minimize the errors. And using this result, we can construct a regression tree that minimizes the errors on the validation set. We simply use the first entries in I and j as any combination of these two vectors minimizes the validation error. Next, let's evaluate how well this model performs on the testing set. Our estimation error plot shows excellent agreement between the estimated and true values, with very low mean squared error of 0.3 and very tight grouping around the diagonal in the scatter plot. Zooming in on the scatter plot, we can see that the model predictions do appear to fall onto horizontal rows. And you can appreciate that there are really only a small discrete set of predictable values corresponding to the set of discrete leaf nodes in the regression tree. We can also display the regression tree which contains a total of 24 decision nodes. The mean squared error of 0.3 we get with a regression tree is much better than we got with a linear model, which was around 70. This demonstrates the utility of regression trees when the relationship between the features and the response variable has discontinuities. There's also a built-in method in MATLAB to test the accuracy of classification or regression trees without explicitly having to create a separate training and testing set. This method is called CV loss, which stands for cross-validation loss. The term loss often refers to the error function for machine learning classification and regression methods. And cross-validation is a process by which different splits of the data set are created to iteratively choose training and testing sets for error analysis. Often this process leads to an estimation of the error that is more robust than simply choosing a single training testing set split, as we did in our example above. To use this function, in MATLAB we can first create a regression tree including both the training and the testing data. We still leave out the validation set because we used it to select our tuning parameters, which we also call the hyperparameters. Then in MATLAB, we simply call the CV loss function with the model as input. And because it's a stochastic process, we can initialize our random number generator before calling it so that we get repeatable results. Here we can see the CV loss function returns 0.38 for our mean squared error. And similarly to the way that we did it, the built-in cross-validation function also confirms the robustness and utility of regression trees when the relationship between the features and the response variable have discontinuities. Other types of nonlinear relationships could include polynomial, exponential, or other types of nonlinear continuous functions. Let's look at an example of a polynomial and exponential relationship. In this case, we define our target as the first feature raised to the power of 1.5 plus the second feature squared plus the natural exponent raised to the power of the third feature plus the species square root. This target is thus a mixed polynomial and exponential function of the features, which is highly nonlinear. We also can add some noise so that the relationship between the features and the response variable is not perfectly a function of polynomial and exponent functions. Okay, let's update our training, validation, and test sets with this new nonlinear target. We can first try stepwise regression and see how well it can handle this type of nonlinearity. As before, we simply call the stepwise function and we use parameters that limit the model to include only the linear terms. And we use the predict method to compute the model predictions on the test set. Let's display the results in a subplot using our estimation error plot function. We can see that stepwise regression struggles with this function with some scatter of the true values away from the diagonal. One can also see what appears to be nonlinearities in the data that are not well approximated by a linear function. The resulting mean squared error is over 2,000. Let's label this first plot as being the prediction by stepwise linear model with linear terms. Well, that seems to be much too long. Let's simplify that to stepwise with linear terms. That's better. Next, let's use stepwise regression again, but allow it to have polynomial terms and see how well it can handle this type of nonlinearity. And a second subplot can display the results. We can see that stepwise regression does better in this case with less scatter from the diagonal and mean squared error of just over 700, which is still not great, but it's much better than the model with only linear regression terms. This makes sense because our target data have a partially polynomial relationship with the features, so constructing a model with polynomial terms should improve estimation accuracy. Next, let's try the regression tree approach that we used before. To give it the best chance, we will retrain our hyperparameters for this new data set. This time, instead of selecting parameters ourselves, let's try out MATLAB's built-in hyperparameter training process. This automatically searches for the best values of the hyperparameters using a cross-validation approach. It's still better to hold out a separate test set when possible, so we'll let MATLAB train on the training and validation sets and hold the test set out for testing later. The training process pops up two new figure windows which show the parameter optimization process. Essentially, MATLAB is searching through potential values of the main hyperparameters to find values that minimize prediction errors when splitting the input data set into training and testing sets. The resulting model we can again apply to the testing set and see how it performs. We can see the resulting regression tree does not do nearly as well as the linear regression model in this case, especially for data points over on the right side of the plot, with lots of scatter away from the diagonal and mean squared error of over 6,000. This demonstrates how, while regression trees are great at handling discontinuities, they are not great at modeling exponential or polynomial relationships. Next, let's try a new method called Gaussian process regression. This approach aims to fit a network of multidimensional Gaussian radial basis functions to the input data set. This is a powerful method for nonlinear interpolation of smooth functions with arbitrary dimensions when given a set of sparse samples as input to fit the function. This is exactly what we have here, a sparse set of data points where we know the value of our function mapping our training features to our training target function. Since the function is polynomial and exponential in nature, it is inherently continuous, which should lend itself well to Gaussian process regression. Gaussian process regression is implemented in MATLAB with the fit-RGP function. We can again let MATLAB automatically select our parameters in this case using the combined training and validation data sets. There are a number of options you can select with this function. To modify how the method selects parameters, here I just tell the method to use a subset of its regressors to select parameters. And again, MATLAB displays two windows that show progress of the parameter optimization algorithms. Then we can use the resulting model to predict values for the testing data set. With Gaussian process regression, we find excellent agreement between the true values and prediction, with little scatter of the true data off of the diagonal and mean squared error of around 4. To summarize, there are many different regression and prediction methods available in MATLAB. We tried several, including linear models, regression trees, and Gaussian process regression. and we discussed and demonstrated some pros and cons of these different methods for different data sets. Similarly to the classification techniques presented in the previous lesson, the regression methods follow the same programmatic process. First, we fit the regression model to the training data using the appropriate fit function. Then the model is available to predict the classification for a new feature set using the predict function. You now have experience with several powerful data regression methods and generally understand how regression methods can be trained and used in MATLAB. This concludes the lesson on Introduction to Data Analysis with MATLAB. If you have followed along, congratulations! You now have experience in basic data analysis techniques in MATLAB. For further reading, for a more in-depth and theoretical presentation of data analysis methods, I recommend the text shown on this slide.